Hey there, it's Shannon MATHCHICK Myers, and today we're looking at series comparison tests. So if you haven't seen them in a while, you might want to brush up on P-series and on geometric series because they are often used as comparison tests. All right, so we'll be learning about the direct and limit comparison tests, and we'll start out with the warm-up. We'll determine whether the series converges or diverges. So for this one, since we have not yet officially learned the direct comparison test or the limit comparison test, what we need to do is use the integral test. Or you could find the series of partial sums and see if it's bounded and monotonic. But I'll just do the integral test for some practice. Cool? Excellent. So step one. Our test is the integral test. Step two, conditions. So we'll write out our related functions. So if f of x is equal to 1 over x squared plus 4, then we need to find out a few things. Is f continuous? Well, let's take a look. We are looking at 1 over x squared plus 4, which has no vertical asymptotes and no holes in the graph because it has x squared and then it's adding a positive number. So no vertical asymptotes, no holes in the graph. It's going to be continuous. On 1 to infinity, and then is f positive in fact f is everywhere positive for the reasons we just talked about. So f is greater than 0 on the whole real line because of the x being squared and then adding 4. And then 3 is f decreasing. Let's go ahead and do a little calculus on this by finding the derivative and seeing if the derivative is negative on 1 to infinity. So f prime of x would equal to, I'm going to look at f as x squared plus 4 to the negative 1. So we'll get negative 1 times x squared plus 4 times 2x, and then my power will now be negative 2 on that x squared plus 4. So we use the power rule and the chain rule. Cool? And so cleaning that up, we will have f prime of x will be 2x, and we'll call that a negative 2x, over x squared plus 4, the quantity squared. Now that denominator is always going to be positive, so let's check out that numerator. We're basically putting in, sure, you could set it f prime equal to 0 and then set that equal to the numerator. And so when x is 0, there's a trending change. And as you see, any positive number that you put in for x, you'll get a negative output. And so that will mean that f is decreasing. I'm just going to put an arrow down on 1, inclusive to infinity, non-inclusive. Groovy? Okay, excellent. So now third step would be to run the test since it meets our conditions. So step 3, run the test. All right, so what we're looking at here is finding the integral from 1 to infinity of 1 over x squared plus 4 with respect to x. Well, that's going to equal to the limit as b approaches infinity of the integral from 1 to b of 1 over x squared plus 4 with respect to x. Now, this is going to be an arctangent result with x will just be x and a squared is 4. So that means that a is 2. We just take the positive. So that will be equal to the limit as b approaches infinity of 1 over a, so 1 over 2, arctangent at x over 2, and that's evaluated from x equal to 1 to x equal to b. And then we'll have the limit as b approaches infinity of 1/2 arctangent b over 2, this in brackets, minus 1/2 arctangent of 1/2 So we will have I'm going to bring out that 1/2. Actually, we can keep it in. So basically, as if you're looking at what the behavior as the arctangent function is approaching infinity, and 1/2 times that result. So remember that you'll get 1/2 times pi over 2. So this limit here the limit here is pi over 2. Now, the limit as b approaches infinity won't affect the other one, so we'll still get minus 1/2 times arctangent at 1/2. And so it'll just be pi over 4 minus 1/2 arctangent 1/2. We don't really care what the result is as long as it's finite. And so for our fourth step, that's our conclusion. The summation as n goes from 1 to infinity of n squared plus 4 converges by the integral test. Agree? All right, so now let's go ahead and take a look. What have we learned so far? What have our tests been so far? that nth term test for divergence. If the limit as n approaches infinity of your sequence that's inside the series is not equal to 0, then the series diverges. If it does, you need to do some more work. You need to run further tests. It's not an if and only if statement. All right, we've also learned about geometric series is of the form, the summation, n goes from 0 to infinity, sometimes it goes from 1 to infinity, of a times r raised to the n. If the absolute value of r is less than 1, then the series converges. So basically, if you have plus or minus a proper fraction, the denominator is less than the numerator is less than the denominator, then the series converges. And its sum, it actually has an infinite sum, is equal to s equals a over 1 minus r. Now keep in mind that sum formula is for when n starts at 0. Otherwise, the series diverges. Telescoping series requires partial fraction decomposition, so make sure you've got that down. And the sum is the sum of the terms which do not zero out, plus the limit as n approaches infinity of the n plus first term of that sequence in the series. A p-series is of the form summation as n goes from 1 to infinity of 1 over n to the p. If 0 is less than p is less than or equal to 1, the series diverges. If p is greater than 1, the series converges. Cool? All right, the integral test requires that f is positive, continuous, and decreasing. For x greater than or equal to 1, and f at n equals a sub n for all n. If the integral from 1 to infinity of f at x dx converges, then the summation from n equals 1 to infinity, it could start later, that's fine too, of a sub n converges. Otherwise, your summation from n equals 1 to infinity of a sub n diverges. Cool? So a little summary there. Now, the direct comparison test. We're going to let 0 be less than a sub n, which is less than or equal to b sub n for all n. Now, if the summation from n equals 1 to infinity of b sub n converges, then the summation as n goes from 1 to infinity of a sub n also converges. So basically, if to show convergence, the idea is you pick a larger series, a series with larger terms, all right, So A sub n is the given series, and B sub n is the comparison series. So the idea is, if the larger series converges, then the comparison series kind of sandwiches in and converges as well. If you think your series converges, choose a larger series, which converges to use for your comparison. Now, if the summation as n goes from 1 to infinity of A sub n diverges, so if the smaller term-by-term series diverges, then that larger series, the summation n equals 1 to infinity of B sub n, also diverges. So if you think your series, this should be diverges, make sure you change that, diverges, choose a smaller series which diverges to use for your comparison. So to show divergence, A sub n is actually it's a sequence. We should change this to sequence here. Because it's inside. The sequence we choose, which is smaller, and B sub n is the given sequence. Cool, cool? Okay, so now how it works. Let's do an example. So using the direct comparison test, we can just call it DCT, to determine the convergence or divergence of the series. First series is A, and I think we got plenty of room for this. So let's take a look. So first of all, when you look at this, you always kind of think about that nth term test. I mean, do you see that the limit as n approaches infinity of 1 over n squared plus 4 would be 0, which means we'd have to run another test. So let's go ahead and we'll just use this one we've just learned about, which is called the direct comparison test. And that can be called DCT. All right. Now, step 2, the conditions. So to use this test, what do we need? We need to pick what are our two, we need to pick our comparison series. Sorry. Still getting over pneumonia. So here I'm looking at the 1 over n squared portion of it, and the fact that we're adding 4, I'm thinking P series would be a good comparison test. So I think this is going to converge, and so therefore I need to pick a series B sub n which is larger term by term, and our sequence inside can just be 1 over n squared, right, which would be our comparison series. or compare the sequence within the summation will be our series, right? So conditions, b sub n is 1 over n squared. I know that converges. We'll talk about that in our conclusion. And a sub n is what's given, 1 over n squared plus 4. So term by term, b needs to be bigger. So, and both of these are positive, by the way, which is part of the requirement. Okay, so a1 is equal to 1 over 1 squared plus 4, which is 1/5. b1 is 1 over 1 squared, which is 1. So a1 is certainly less than b1. And then a2 would be 1 over 2 squared plus 4, so that would be 1/8. And b2 would be 1/4. And so that's certainly less than or equal. And I think this will continue, right? Because you keep adding 4 to a sub n, which is going to make that denominator smaller. So we have a3 will be 1/13, which will be less than or equal to 1/9, which b3 is. And that'll go on and on. So yes, that is true. Cool, cool? Okay, so step 3, run the test. So that actually won't be very hard. The hardest thing here are the conditions. So when we run this test, we're basically just stating that the summation from n equals 1 to infinity of 1 over n squared is a convergent p-series with p equal to 2, which is greater than 1. So now our conclusion, last step, conclusion. The summation as n goes from 1 to infinity of 1 over n squared plus 4 is converges by the direct comparison test. Cool, cool? Excellent. All right. So now let's look at part B. We've got 3 to the n over quantity 2 to the n minus 1 into quantity. So I don't know about you, but to me this looks a bit geometric in form. So our comparison test, and I think that this one is going to diverge because the 3 to the n is going to be larger, then that numerator is going to end up beating out that denominator, I believe, as time goes on. So let's see what we got. We are going to, I believe that the direct comparison test will work because my comparison series that I have for my evil plan is the geometric series 3/2 raised to the n. So step 1, what's our test? Our test is the direct comparison test. Step 2, conditions. So this time we have to pick a series which is going to be smaller than the given series. So the sequence we'll pick, our a sub n, is going to be 3/2 to the n. And if you put a summation with that, it's a divergent geometric series. And that has positive terms. And then our b sub n is our given sequence, 3 to the n over 2 to the n decreased by 1. That's also greater than 0 for n greater than or equal to 1. Part of step 2 is still conditions. And so let's do a comparison. Now, A1 still needs to be smaller, right? So let's check it out. A1 is equal to 3 halves to the 1, which is just 3 halves. B1 is going to be 3 over 2 minus 1, which is just 3. So this is still working. We want this to be true. It's part of our conditions. So A2 will be 9/4. And then B2 is going to be 3 squared, which is 9, over 2 squared minus 1, which is 9/3. And that is 3, right? Which is greater than 2 1/4. And it'll continue in this way. We'll do one more. A3 is going to be 27/8. And B3 will be 27 over 7, right? So you've got the same numerator. The less the denominator is, the bigger the number, right? And so that is our B. Sorry, these shouldn't be BNs. They should be B1, B2, and B3. So that will continue that trend. So yes. So the conditions are met. Now, step 3, run test. And so the summation from n equals 1 to infinity of 3 halves to the n is a divergent geometric series with R, absolute R, equal to absolute 3 halves, and 3 halves is greater than or equal to 1. That's showing divergence. And so, step 4, conclusion. The summation from n equals 1 to infinity of 3 to the n over 2 to the n decreased by 1 diverges by the direct comparison test. Cool, cool? All right, excellent. Now, the limit comparison test is also very groovy. A lot of people prefer it to the direct comparison test because you don't have to figure out which one's bigger term by term or which series is smaller term by term or sequence is smaller or larger. So here we go. If A sub n is greater than 0 and B sub n is greater than 0, so you just need 2 positive term sequences, and the limit as n approaches infinity of the ratio between the 2 sequences is equal to L, where L is finite and positive, then the summation as n goes from 1 to infinity of A sub n and the summation as n goes from 1 to infinity of B sub n either both converge or they both diverge. Groovy? All right. So note, when choosing your comparison, you can disregard all but the highest powers of n. So if you're using, like, say, a p-series, you just you just look at those leading terms. So in the numerator and the denominator. So if we are testing the summation as n goes from 1 to infinity of the square root of n over quantity 5n squared plus 2, our comparison series would be the summation as n goes from 1 to infinity of root n over n squared, which is equal to the summation as n goes from 1 to infinity of 1 over n to the 3 halves when you divide those like bases. Cool? All right, so here we go. Using the limit comparison test to determine the convergence or divergence of the series. So step 1 for A, and then we'll have so this is which test, and we're using the limit comparison test. Which we can just call LCT. Step 2, you'll like this part. Conditions. Okay, so let's just let A sub n be the given sequence, n over n to the 4th plus 2n squared plus 1, and then B sub n can be equal to n over n to the 4th, which is 1 over n cubed. Put that one in a summation, you'll get a convergent P series, right? So, step 3, run the test. You'll have to use your mad limit skills. Yes, I expect you to work it out. So the limit as n approaches infinity of the ratio of these sequences will be n over n to the 4th plus 2n squared plus 1. And then I'm going to multiply by the reciprocal. Is that okay? So we're dividing by 1 over n cubed. But just to have it nice and clean, we'll multiply by n cubed over 1, which of course is just n cubed. Now, this in turn will be the limit as n approaches infinity of. We will have n to the 4th over n to the 4th plus 2n squared plus 1. Now to do it properly, we'll divide each term in the denominator by the highest power of the denominator, and to even it out, we'll do the same to that numerator. And so this is going to give us the limit as n approaches infinity of 1 over 1 plus 2 over n to the 4th, n squared, plus 1 over n to the 4th, and that limit will have a result of 1 over 1 plus 0, which is 1, which is finite and positive. Cool? So, our conclusion, step 4, actually, you know what? We have one more thing we need to say here. So, the summation as n goes from 1 to infinity of 1 over n cubed, our comparison series, is a convergent P series, P is equal to 3, which is greater than or equal to 1. And so now we have all of our pieces for our conclusion in step 4. The summation, as n goes from 1 to infinity, of n over n to the 4th plus 2n squared plus 1 converges by the limit comparison test. Groovy? Okay, so now let's go to the next one, do another example. And with this one, we have to put a little bit of initial thought into this, okay? So sine at n has to be between -1 and 1, right? So if you add 1 to that, you'd have 0 less than or equal to 1 plus sine n, which will be less than or equal to 2. Now we can take away that inequality because we're not going to end up with 0 or a multiple of pi in our summation, in our, when we plug in, because we're plugging in integers. So 0 can come out, and so basically our numerator is bound between 0 and 2. All right, so you can basically consider that to be a small positive constant, right? So keeping that in mind, for our test, we will use the limit comparison test, conditions. I'm looking at that 1 over 10 to the n, right? And thinking geometric series. So our a sub n, actually this is conditions. So under our conditions, we'll put what our sequences are. A sub n is 1 plus sine at n over 10 raised to the n. And that is greater than 0 for n greater than or equal to 1. Our b sub n will be 1/10 to the n, which is also greater than 0 for n greater than or equal to 1. So step 3, run the test. We will have the limit as n approaches infinity of, we have 1 plus sine at n over 10 to the n, and then I'm going to do that invert and multiply business, which means we'll have 10 over 1, which is 10, to the n. Cool, cool? So now, for the reasons we talked about, so these divide out, right? And for the reasons we talked about, that limit as n approaches infinity, it's going to be bound between 0 and 2 non-inclusive. I don't think it will equal to 2 either in there. So we can take the inequality off that. And so they're either going to both converge or both diverge. So now let's take a look. We're going to have our comparison series. So the summation as n goes from 1 to infinity of 1/10 raised to the n is a convergent geometric series r is equal to 1/10 and 0 is less than absolute 1/10, which is less than 1. And so now for our conclusion, we can say the summation as n goes from 1 to infinity of 1 plus sine at n over 10 to the n converges by the limit comparison test. Groovy? Okay, so that's it for today. I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And hey, if you like what I'm doing, why don't you hit that subscribe button, the like button, and you go ahead and share the video with other people studying math. Bye.